don't need these two components. Just have a one-by-one matrix, if you like, just a single component wave function. You don't need to talk about components. It's just a wave function, right? So you just work with your one component wave function. If your H is spin independent, if there's no term in your Hamiltonian that's to do with spin, right? I have an ordinary kitchen chair now, so I'll turn this around for the second half of this session. Now, conversely, say now our two-component wave function that where the Hamiltonian in general depends on the spin and the position. So there are terms like the kinetic energy depend on the velocity, and the potential energy like V would depend on the position, stuff like that. But say this now, the Hamiltonian does not depend on the position. So we're not talking about R, we're just talking about S, the spin, that's all. Only spin. So I've put an S here. So the Hamiltonian now is limited to only spin. So in that case, we have an upstate and a downstate eigenfunctions. Right? So we need a two-component wave function here. Now, because this has nothing to do with position anymore, we can get rid of the R term in these A's, or the psi 1, so it's just now purely a function of time. So we'll just call it A of t, B of t. And here's your Schrodinger equation then, when your Hamiltonian does not depend on the position. Right? It depends only on spin. Okay, so you've got that kind of thing. So your spinner, remember this eigenvector, this two-component eigenvector called a spinner, a spin vector spinner, right? So, and it will depend only on the time. So you can put a t here, as I say. Now we didn't deal too much with putting time here for the spinners, because the two states up and down, they had identical time dependence. Don't worry about that too much. It's just a detail. All right, now now we come on to well, we're not finished with spin in effect. Look on spin as a kind of angular momentum, special kind of angular momentum. And now we're starting to talk about angular momentum in the context of several or multi-particle systems. So then you need to start thinking about how do you add angular menta, plural. How do you add angular momenta in that context when your quantum system is a multi-particle system? For example, there might be two particles involved, so you have like two spins. Or you might be talking about one particle that has spin and its orbital angular momentum. So it's S hat, its intrinsic spin, or just spin, and its orbital angular momentum, L. So you need a wave function that then combines those two kinds of angular momentum, right? Orbital and spin. So here we're just starting an important branch of quantum mechanics that deals with the addition, summing, the addition of angular momenta, and it gets very elaborate. There are I have books, not just chapters or sections. I have books on this topic, on the addition of angular momentum. It can get quite heavy, mathematically heavy. All kinds of symmetries involved and group theory, right? So definitely not undergrad stuff, but we can start. Give you, this is an undergrad course, right? Maybe it's your first quantum mechanics course, so you expect that a certain amount of introduction, giving you a taste of what quantum mechanics is about. So here's a kind of foretaste, leading into it, of how you go about adding angular momenta in quantum mechanics. So I was saying a little bit before, but for example, in the case of an electron, so your quantum system you're talking about, you're applying quantum mechanics to, you're finding its eigen equation, its Schrödinger equation, all that stuff. Now, if it's an electron, I'd say a single system, just one particle. But if you're talking the full angular momentum, you may have its spin angular momentum and its orbital angular momentum. Or you might have an atom that has several electrons. Right? It's not the hydrogen atom. It's an atom with more protons than the hydrogen atom nucleus has. And so there'll be several electrons, right? So several spins. So how do you go about handling the quantum mechanics of a multi-particle system with spin, stuff like that, right? Now, in classical mechanics, you add angular momentum vectorially. You just add the two vectors, right? In the usual place the tail of the second arrow at the position of the tip of the first arrow, and the resultant vector sum will be the arrow from the tail of the first arrow to the tip of the second arrow, right? A vector sum. Well, that's how you do it in classical mechanics when you're adding angular momentum. But in quantum mechanics, things are more subtle, more complex. And so we'll start in the next session, next board, this is the end of the board. We'll start in the case where we have two spins. Right? So we have two identical particles. Now we've talked a bit about identical particle wave functions in the past. The symmetric and anti-symmetric form, if you remember. So we're going to do a bit of quantum mechanics now in the context of adding angular momenta, but the angular momenta we're talking about in this particular case will be spin. So we have two identical particles, one with spin 1 and the other with spin 2, and we'll start doing the quantum mechanics of that two identical particle system, both with spin, S1 and S2. Right? So that'll be for the next session.